Hi everybody, I am Andrea Daddabbo, the chairman of Group 11, and I am going to present you our project. It is the study of the vibrations of a V8 cross-plane crankshaft. At first, we will see the team composition. Then we will go through the definition of the problem, the theoretical model, the numerical implementation on MATLAB, the results achieved on MATLAB, and through an analysis of the engine sound. Then we will see the conclusions. Starting from the team composition, our coordinator was Simone Di Corato. The theoretical development was carried on by Alessandro Leone and Giuditta Cascella, while the numerical implementation has been done by Andrea Saponaro and Giorgio Crosti. Finally, Francesca Milito worked on the graphic side, while our jolly role was given to Raffaella Sibilia, and it has been focused on the sound of the engine. At first, it is necessary to identify two types of V8 engines. In the flat plane type, crank pins are spaced at 180 degrees interval, and the firing order goes from bank to bank. This configuration is lighter and smaller, can rev up faster, but has problems related to the imbalance of secondary forces. On the other hand, cross-plane crankshafts have crank pins spaced at 90 degrees intervals, with a cylinder always fired on the same bank of the previous, at least once per bank. This alternative is heavier and larger, rotates slower, and is featured by the imbalance of primary forces. The model we have chosen is the Ford Boss 302, mounted on the Ford Mustang MY69. It has been considered as a 6 degree of freedom rigid body, and a 3D model of the engine has been realized on Autodesk Inventor thanks to technical data. The development of the theoretical model for the forcing starts from the kinematic of the CRANK-CONROD system. After deriving the expressions for the displacement of the piston as a function of time, by making appropriate hypotheses, it is possible to generalize this formula for all the 8 pistons. Eventually, what we did was to use this expression in MATLAB and derive it twice to obtain the accelerations of the pistons. We consider a simplification for the calculation of the forcing, which is that each force acts on a fixed application point at each instant of time. This point is in the middle of each cylinder axis, at a distance y0 above the COG and at a coordinate zi. Then the expressions for the forces along the three axes have been obtained as shown in figure. Moments have been evaluated by the product between the forces and the respective perpendicular distances from the application point to a plane that contains the COG of the engine. Then, to derive the equations of motions, we decided to use Lagrange's equation, particularly useful when both linear and angular displacements are to be considered. Here, we reported the expressions for the total kinetic energy, for the total potential energy, and for the Rayleigh dissipation function. Subsequently, we derived the equation of motions, which can be written in matrix form. The three matrices, namely mass, stiffness, and damping, are shown in these slides. To solve the vibrational problem and find natural frequencies and modal shapes, we decided to use the DUNCAN approach, which provides the solution for a generic dump system and works in the phase space. At first, the free vibration problem was considered to find eigenvalues and eigenvectors. In particular, 12 eigenvalues and eigenvectors have been found, which is in accordance with the theory, and we checked they were pairs of complex conjugates. After finding natural frequencies and mod shapes, which have been arranged in the modal matrix, it is possible to solve the force problem. To do so, you take advantage from the orthogonality conditions, and finally, from the convolution integral to determine the solution in time domain. Eventually, we have determined the expressions of the coordinates for each mounting, in order to compute the forces transmitted to the chassis, as a sum of a contribution due to the springs and another one due to the dampers. Define the path to be followed on MATLAB, we start by defining the parameters of the system. Stiffness of each spring and damping coefficients have been determined by technical datasheets and from literature. The first thing to be done is the definition of time and space variables. In particular, it must be pointed out how important is the number of points for the computational cost and time, which is something we will touch in a while. Then, all the matrices necessary to solve the problem have been translated into MATLAB code. Here it is shown the mass matrix, here the stiffness matrix, here the damping matrix, and here the two matrices we need to solve the Duncan approach. Eigenvalues and eigenvectors with natural frequencies have been easily determined thanks respectively to the Eig function provided by MATLAB and to the expressions we saw in the theory. Then, the calculation of forces and moments has been implemented. Only some parts of the code have been reported on these slides to make the presentations as clear as possible. Here are shown the moments implemented on MATLAB. Damping ratios have been calculated with the formulas in the theoretical model, and they have been used to determine the time response by applying the convolution integral. In the end, the code for the forces transmitted to the chassis has been written and implemented on MATLAB. After double-checking the code multiple times, simulations have been carried out to see what the results were. In particular, concerning the inertial forcing, we decided to plot forces and momentums for the two scenarios, by considering all the harmonics of the expansion and by considering only the ones up to the second order, a simplification that comes from the crankshaft being crossplane. From these results, it is possible to see how the crossplane engine is well balanced, as the intensity of forces and moments is very low. Here, the results in terms of natural frequencies and modal metrics have been reported. Then, the full transient responses in terms of rotations and displacements of the COG, and also in terms of its accelerations, have been plotted. It must be said that the shape of the displacement on the z-axis and of the rotations around the x and y-axis have an atypical shape that is related to some numerical errors of the software. These errors can be appreciated in these slides and are related to the number of points we have chosen to run some simulations. Here, also the plots of the forces transmitted to the chassis for the speed draft conditions have been plotted. Finally, we had to select three regions of interest to plot the time histories and spectra in steady-state conditions. In particular, we have chosen to carry out this final analysis at 5800 RPM, which is the maximum power regime, at 2600 RPM, which is the maximum torque regime, and at 3000 RPM, which is the highway regime according to datasheets. Here it comes to some considerations of the computational cost. For a low number of points, some numerical errors are likely to appear, as shown in the top right image. The solution to the problem is raising this value, as shown by the figure on the bottom right. Nevertheless, the time required for the simulations to complete is higher and higher as the number of points increases. Therefore, we have decided to initially run simulations both with a higher and lower number of points, in order to test out this point. More accurate simulations with even higher number of points are already running to show better results. There is an example of numerical error due to a too low number of points, since these plots should have straight and more uniform appearance. Spectra have been then plotted to evaluate the energy content of each signal. This was possible thanks to the Fourier transform, which takes a time-dependent function and transforms it into a new function of either the natural circular frequency or of the natural frequency. As seen in the theoretical lectures, this operator works also for the inverse transformation. Here, the mounting behavior in terms of forces, accelerations, and spectra of the forces is reported for the maximum power regime. These plots instead have been obtained with a high number of points, and indeed they show no numerical errors, and this is an analysis that has been carried out for the maximum torque regime. The results also for this regime and for the highway regime are shown in these following slides. Finally, we have decided to analyze the importance of the sound in the engines. Sound is used from car makers to convey emotions and traits associated with their brands, up to the point that some cars have a sound which can be recognized by miles, and that is a symbolic mark of the model. The analysis of all the components affecting the perceived sound is known as NVH. Shifting to our case, a comparison between cross-plane and flat-plane sound is reported in the following slide. frequencies arise from the firing order, which turns into a darker, richer, and less pitched sound for the cross-plane engine. On the contrary, the ideal tune of exhaust pulses in a flat-plane engine allows for a timbre that is smooth, particularly at high revs, and it's also highly pitched. In the end, the project has led us through the analysis of a multi-degree of freedom system and through the formulations of the theoretical model beyond the numerical simulation of an engine. The importance of computational cost and time has been considered. Moreover, a focus on the sound of the engine has been done to understand in a better way the differences between flat and cross-plane V8 engines. I have concluded. Thanks for the attention.